Hi, my name's Ram, and I'd like to go over Kruskal's algorithm. And what we want to remember is, of course, there's this idea of something being a spanning tree, which is where you have a graph and it's a weighted graph, and you're able to produce a spanning tree of that graph where in the resultant tree, you have all of the nodes of the original graph, but exactly v minus 1 edges. That's a spanning tree. And of course, because it's a tree, it can have no cycles. So therefore, you have a graph that has v minus 1 edges, has every node present, because of course it has to have every node present if it spans the graph, but it also has no cycles. Having no cycles is simply characteristic of a tree in particular, or in general, rather. So it's not so much a prerequisite for a spanning tree as much as it is a property of a tree in general. So a spanning tree, again, it's important to remember exactly v minus 1 edges, and it will most certainly have each and every node of the original graph, the weighted graph that is, and it will not have any cycles. But then, of course, we conceive of this idea of there being something called a minimum spanning tree, in which case it's a spanning tree, and there can be many, where the weights of the graph are minimized. In other words, you conveniently end up removing the edge of the tree such that the overall weight is as minimum as it could possibly be. Kruskal's algorithm is a way to generate a minimum spanning tree for a particular graph. Now, you'll remember that Prims is also a similar technique or algorithm to generate a minimum spanning tree, and Kruskal does not necessarily have an advantage over Prims in the sense that Kruskal does not beat Prim in terms of time complexity. They're both order of E log V, and we'll see why. But, and the problem statement is the same. So they are actually two different algorithms that end up solving the same problem in the same amount of efficiency. So we're set to build a minimum spanning tree given a graph in O of E log V time, similar to Prim's. And what we do here is we maintain a priority queue, right? And the priority queue, in this case at least, will hold edges and not necessarily nodes. So it takes all the edges it can, right? And then it puts them into a min heap. And so in that sense, you have a min heap that has O of 1 access to the root of that heap, which is the minimum or smallest edge cost. So it takes in all the edges, puts them in a min heap, and keeps the smallest edge cost at the top. And so, of course, Kruskal is functioning in the world of edges instead of nodes. And you'll see that it will then take those edges and reconstruct the tree by, if you want to use the language that we used in the coin change video, constantly issuing the smallest amount edge. In that case, it was coin, but here it would be edge. And it builds the tree out of a forest of nodes. Now, I want to kind of stop there because it's complicated to say a forest of nodes. But really, what I mean to say here is when you consume a graph, Kruskal will basically create a kind of a forest for those nodes where there are no connections between them, and each node just kind of belongs in its own world. It creates sets of nodes where each node is in its own set initially. So, if you had a graph, a complicated graph, we're going to soon devise a way, which is, of course, the beginning step of Kruskal, to have all of the nodes in their own set. And then it will pull from the priority queue, take min edge weight, and know of one time, because, of course, that's what a heap allows. And then it will reconstruct this graph, right? It will start assigning edges to nodes such that after it hits the max quantity of v minus 1 edges, which is, of course, the maximum not maximum, but it's precisely the amount of edges you need for an MST. As soon as it hits that n-1 range, it will then terminate. So build an MST given a graph in O of E log V time, same as Prim's, maintains a priority queue, a min-heap of edges, and then it assigns those edges to nodes beginning with a singleton set. So that singleton set is the version it's the output where each node gets its own set, and it will only add the edge between nodes if they belong to different sets, right? There will be a check there where, well, I'm trying to add an edge here, but do these nodes belong to different sets? If they're of the same set, then actually I'll end up introducing a cycle. And then, of course, we will negate what I mentioned before, which is you cannot have a minimum spanning tree, or a spanning tree for that matter, that has a cycle. So you might say, well, gee, why is that, right? If they're in the same set, well, then I'm just adding an edge. Why does it really matter? Well, that's not true, right? So imagine A, B, and C, right? If you have A, B, and C, and there are already edges between them, you introduce a new edge. A and C are already connected. If you add a new edge, then they're already in the same set. That creates a cycle. So in that sense, there are, of course, key tenets here. Kruskal is building an MST. It's doing it in the same time as Prim does it. And of course, it uses the same data structure, a min heap. But what's in the min heap are edges instead of nodes. It starts off with a singleton set and then assigns edges by pulling the minimum edge from the heap in O of 1 time. And then it checks, are the nodes I'm going to assign the edges between already in the same set? If they're not, I will do it. That's sort of the core premise. Now, I've talked about certain things. Let's parse them out. I said you need to let a graph be the input for Kruskal. And then you need a singleton set. You need a way to basically make each node a set of its own. And then you need to, so that in a sense is a requirement. So I actually made a line here. It says data structure to support this. Void make set int n. Right? Take in nodes, and you need a make set function. So you can actually create and devise this singleton set. Then you need a find set function, right? You need to be able to say, can I input a node at hand, and can I figure out which set this belongs to? Why is that important? Well, because of course we need to be able to compare, is this node I'm trying to attribute an edge to already in the same set as another node? If I can't introduce an edge between two nodes in the same set. So find set, which edge something belongs to, now becomes relatively important. Union. I need to be able to union two nodes, right? I need to be able to connect two nodes together. If in fact they're not already a part of the same set, it would make sense to connect them. So those are the three core methods you want to think about it to then, of course, execute on Kruskal's algorithm. Now we'll see one by one how this is done. Make set. Well, our implementation here will simply be an array where we take in where the relationship between index and the value at that index is so the index are the node values, right? And the value that the index refers to is the set to which the node belongs. So 0 belongs to 0, 1 as a node belongs to set 1, 2 as a node belongs to set 2, 3 as a node belongs to set 3, 4 as a node belongs to set 4, 5 as a node belongs to set 5, and so on and so forth. So if I'd have changed 1 to 2 here, well then 1 would have belonged to set 2. So that's kind of the correlation for make set. And what I just described, this belonging here, actually captures the union operator. union. All you're supposed to do is go to the node you want. Okay, you want 1 to be in set 2. Go to array of 1, set it to 2. You want value 5 to be in set 7. Go to array of 5, set it to 7. That captures the union operator, right? Set it to what you want it to belong to. Yeah, the find operator actually ends up being a little bit more complicated. Um, you want to find out what set a particular node belongs to. Um, and let's say I need to do find of 1. Well, okay, well, 1 belongs to set 2. Well, there's kind of a different array that would make sense in order to illustrate this, but let's just kind of mess up the numbers here. Let's say I want to find 1. 1 belongs to 2. 2 belongs to set 5. 5 belongs to set 5. Right? So that's the relationship there. 1 belongs to set 2, right? What does 2 belong to? 2 belongs to 5. What does 5 belong to? 5 belongs to 5. So that means 2 and 3, sorry, this number here is actually also in set 5. So if 1 belongs to 2 and 2 belongs to 5 and 5 belongs to 5, then everything is under the umbrella of set 5. So what you're doing with the find operator is you're starting at the array you want, and you're doing kind of a trace all the way down to a halt condition, which is where you find out whether or not you're at a position where the array index is the same as the parent. So that ends up being in the worst case order of n, right? You can imagine, because there is a world in which we might have to do this for the extent of the array. But those are nevertheless the 3 operators of make, set, union, and find to support Kruskal. Now, we can, of course, extend the conversation to talking about their time complexity. Make set is, of course, linear. You simply are able to capture, you're able to create an array and then populate it with how many values you have. And at that point, in the worst case, it would be order of V. And that is just going to be true for any input n that you have. Find can also be linear in the worst case. If you have to trace a long chain, you can imagine, right? Doing this kind of jumping behavior is certainly something that takes consumption. Union is constant, right? Basically taking a number and setting it to another in terms of the parent-child relationship is, of course, an O of 1 operation. But ultimately, you might have to actually find the element first in order to actually make that change. And we know find in the worst case is order of V, and therefore, in the worst case, union has an order of n, or in this case, the equivalent is order of V because V encapsulates how many nodes we have. So we ask ourselves, can we optimize find? And there are 2 such methods to do that. First is path compression, right? Path compression is, in a sense, what we spoke about before, and I'll tell you precisely why. Path compression says, well, look, you have an array here. That's great. That's excellent. But, let's say you wanted to do find of 1, right? You would likely end up developing kind of a chain, right? So you go 0 of find of 1 would be, okay, well, what is the halt condition? The halt condition is precisely where I end up in a position where the index equals the array value that's there. So I do one of what does one belong to? Okay, it belongs to set two. What does two belong to? It belongs to set four. What does four belong to? Or it belongs to set five. What does five belong to? It belongs to set five. So finally, we've come up to a point where the halt condition now matches. And everything beforehand is actually in that set because, again, there's subsets of that larger set. And so what path compression tells you to do is, hey, just go and change these numbers to 5, to that root value that you got from where you found that the array index value matches the value there. And everything before that must, of course, be in the same set. So let's say next time if I wanted to do find 2, well, that would be very simple. It would just simply give me precisely what I want in order of 1 time without actually bouncing around the chain. Now, that is, of course, not true in terms of all cases. It's order of 1. If you kind of, you're improving the chances that it's order of 1, but it's not order of 1 in all cases. And so it's still order of n in the worst case. So this alone is not enough. Path compression alone is not enough to do the trick. We have another way. It's called union by rank. And these are actually supposed to be used more or less in tandem. What you want to understand in terms of rank is the height of a tree is called a rank. When you kind of create these chains, in a sense, you're creating a tree. And if you have a large tree, you can imagine that if you have a large tree, or instead of large, I'll go ahead and say a tall tree and a small tree. There are 2 ways you can combine both of these sets. You can union them in a number of ways. You could make this the child of that tree, so this is kind of on top. You could make that the child, right? Now, the idea you can intuitively understand that the height of the tree remains the same if I take the smaller tree and make it a child of the root of the higher tree. So if rank is synonymous with the height of the tree, union by rank says take the smaller tree and make its root the child of the tree of the larger rank. Which, of course, reduces traversal time because the tree is consistently the same height, and therefore you no longer have to actually traverse a higher tree, which helps in terms of time complexity. The algorithm is simple. Edges accepted is 0. We create a disjoint set so that we get the singleton tree that we spoke about before. We pass in the number of vertices that we have, initialize a priority queue. Nothing yet is costing us time. Add all edges by cost to the priority queue. We know that adding anything into a min heap is log v. And because we will execute this is an iterative loop, certainly, to be able to add these edges to a priority queue. But if we add all the edges by cost to a priority queue, well, we would be doing that e times. So e edges, a log e cost per addition, it's e log e. Or sorry, e log v. Or we're adding all edges by cost. So actually, we're iterating e times. And because the height of the tree is represented by e, it will be O of e log e. Now here you have, while the edges are less than num, the number of vertices that you accepted minus 1, which of course makes sense that this is not num of v, because again, the halt condition when we're done building the minimum spanning tree is when there are v minus 1 edges. Until that's true, we dequeue an edge, presumably the smallest, because that's at the top of the min heap. That's a log e time. By the way, the whole loop runs e time, so just keep that in mind. The whole loop runs e time, and we have an e here, a dq, so that's already an e log e. This we've already kind of optimized, but nevertheless, find out which set the first node belongs to and the second node belongs to. And if they're not in the same set, well, keep a count of how many edges you've accepted into your solution, and then union both of those sets. So not anything too difficult. Counter for edges accepted so that the loop can execute. Create a singleton set. Initialize the priority queue. Add all the edges. This is where we get our first cost. We'll e log e edges for the priority queue, right? It will iterate e times. And each addition is log e, so e log e. And then execute until we hit the halt condition, num of v minus 1. We only want v minus 1 edges. By definition, that's how much we need for minimum spanning tree. That runs e times log e each time it runs, e log e for the loop. Find out if they're both in the same set, just in case you're appending a cycle. If they're not, great. You're clearly adding an edge, so take that into account so that your while loop knows when to terminate. And then, of course, union both of those sets. So we're actually looking at an overall big theta runtime of e log e. And then that concludes Kruskal's.